Welcome to the Deep Dive Physics. Today we're going deep into the world of vectors and forces.
The foundation of how things move, really.
Yeah, exactly. The foundation of how things move and interact in our universe. But before we get going, if you like these deep dives into all sorts of fascinating topics, hit that like button and subscribe to the Deep Dive channel.
Always appreciate it.
So let's dive in. Today we're starting with something that might seem a little out of place. Symmetry.
It's not just for art class.
Huh, right. Definitely crucial in physics. I was reading about Professor Herman von Weyl. He defines symmetry as something staying the same, even after you do something to it.
It's a good place to start, I guess.
Mm-hmm.
For physics, symmetry is all about the laws of physics themselves. Like, they stay the same no matter where you are or how you look at things. Imagine like a really complex physics experiment, right?
Okay, yeah.
Now imagine building an exact copy of that experiment somewhere else. Would you expect the same results?
Well, yeah, I think so. I mean, assuming you took everything into account.
Right. Assuming you moved all the relevant factors, too.
So does this mean there's like no absolute position in the universe? Like everyone's coordinate system is equally valid?
Exactly. Think of it this way. There's Joe, setting up his experiment with his coordinate system.
All right, there's Joe.
Then Mo comes along and sets up his own system, maybe offset a little bit from Joe's. Newton's laws, they would hold true for both of them.
Even though their measurements might be different?
Precisely. That's translational symmetry in action.
Okay, that makes sense.
Yeah.
But what about something like a grandfather clock?
The grandfather clock.
Yeah, wouldn't it work differently if it was tilted? Seems like that breaks the symmetry, right?
That's a good point. You've brought in an external factor there, Earth's gravity.
Oh, right.
Tilting the clock changes how gravity acts on the pendulum. Now, if we rotated the entire setup, the clock, and the Earth's gravitational field,
Oh, I see.
then the clock would function the same. This is rotational symmetry.
Ah, okay, so it's like the laws themselves are symmetrical, but then those external factors like gravity, they can make things seem wonky.
Yeah, exactly.
It's like a hidden order, kind of.
Yeah.
Pretty cool takeaway for our listeners. Now, how do vectors fit into all this? I know they're supposed to be like really important for dealing with these symmetries.
Vectors are like the language we use to navigate this symmetrical world of physics.
Okay.
They describe quantities that have both magnitude and direction. Think about taking a step, you've moved a certain distance, but in a specific direction.
Right, a displacement, yeah.
Exactly. That makes it a displacement vector. It's represented by 3 numbers.
3 numbers for a single step.
Well, yeah, you need 3 numbers to describe both how far you moved and in which direction.
Makes sense. But dealing with all those changing coordinates can get a bit messy, no? Do vectors make that any easier?
Absolutely. That's the beauty of it. The same vector symbol represents the same physical quantity no matter which coordinate system you're using. It really simplifies the equations.
Okay, I see. So what kind of things in physics are represented by vectors?
Oh, tons of things. Velocity, momentum, force, acceleration, just to name a few.
So anything that has both magnitude and direction.
Exactly. And we can visualize them as arrows, right?
Yep.
The arrow points in the direction of the vector, and the length of the arrow represents the magnitude.
Right, that makes sense. But how do we actually know that something like velocity is a vector? I mean, it seems intuitive, but...
Well, we know it's a vector because when we change coordinate systems, the components of velocity, they change according to the same rules that govern position coordinates.
Interesting. So there's a mathematical basis for it, not just our intuition.
Precisely. And here's another cool thing. The derivative of a vector is also a vector. This means, like, if you differentiate a position vector with respect to time, you get the velocity vector.
Oh, okay.
And if you differentiate the velocity vector, you get the acceleration vector.
Now we're talking. Doesn't this tie directly into Newton's laws? Can we rewrite them using vectors?
You got it. Let's take Newton's second law, F. Force and acceleration, they're both vectors.
Right.
So we can write this law as a single vector equation.
Wow, efficient.
This one equation elegantly captures 3 separate equations, one for each component.
That's really cool. But this brings up a question about force itself. I mean, we have this neat equation, but what is force, really?
That's a really deep question, and honestly one that physicists are still grappling with. Mathematical frameworks like Newton's laws are powerful tools.
Right.
But they don't fully define what force is.
So understanding force requires us to go beyond FMA. Consider its inherent properties, not just the math. Something for our listeners to ponder on.
Exactly. It's tempting to think that force always originates from physical bodies, right? Meaning no body, no force.
Okay.
But that leads you down a rabbit hole of circular definitions.
Oh, how so?
Imagine someone comes up with a term, say, Gorse, to describe an object's rate of change of position. Then they declare, if an object is changing position, a Gorse must be acting on it. But that's not really an explanation, is it?
No, it's just shifting definitions around.
Exactly. It highlights the need for precision in our definitions.
Does that mean physics is all about approximations?
In a way, yes. Think about something as simple as defining a chair.
Okay, a chair.
Even that involves approximations.
Right.
What exactly makes up the chair? Are dust particles on its surface part of it? The air molecules constantly bouncing off it? The real world is messy. Physics tries to describe it with increasing accuracy, but there's always some level of idealization.
So unlike that abstract perfection of mathematics, physics is about grappling with the messiness of reality.
Precisely. Math, it doesn't care what we're talking about, only that the logic holds true.
Yeah, it's abstract.
Physics, it applies that logic to the real world. We have to deal with its limitations.
That's a good way to put it. Speaking of messy realities, let's talk about friction. It's like this force we encounter every day, but it always seems to be messing up our nice, neat equations.
Friction is a fascinating beast. For a long time, we thought it was all about surface irregularities, like tiny bumps catching on each other.
Yeah, okay.
But modern physics has shown us it's much more about the interactions happening at the atomic level. Atoms vibrating, bonds forming and breaking, heat being generated. It's an intricate dance.
So even something as simple as friction has these deep, complex origins. Are there any simplified rules we can use to describe it? At least approximately.
There's this handy empirical law, F equals mu n. It tells us that the force of friction is proportional to the normal force pressing the two surfaces together. Essentially, the harder you push two things together, the harder it is to slide them past each other.
Okay, that makes sense intuitively. But there's that proportionality constant there. Mu, the coefficient of friction. Is that truly constant?
Well, in reality, it's not truly constant. It varies depending on things like the smoothness of the surfaces, whether they're clean, even the speed of the objects.
I see.
But for practical purposes, we often treat it as a constant.
What about that idea that it takes more force to get something moving from rest, like static friction,
Yeah.
than to keep it sliding, like sliding friction?
Mm.
Is there any truth to that?
With dry metals, it's surprisingly difficult to prove definitively. This idea might come from our experiences with things like lubricants or flexible supports.
Okay.
They create a sort of binding effect. But with clean, dry metal surfaces, the difference between static and sliding friction could be negligible.
So if I wanted to predict the friction between two substances, can
Yeah.
I just look up that coefficient of friction and plug it into the equation? Seems simple enough.
Unfortunately, it's not quite that straightforward.
Oh,
Let's take copper sliding on copper as an example. You'd think it would be simple, but it's not. Contaminants on the surfaces, they play a big role. And if you try to create perfectly pure copper surfaces,
yeah.
they actually adhere strongly to each other.
Really? Clean copper sticks together. Why is that?
It's because, at the atomic level, they recognize each other. You see, when there are contaminants like oxides or grease between them,
Yeah.
the atoms, they know they're different. But with pure surfaces, they essentially think they're part of the same piece of material and form strong bonds.
That is wild. Do you have like a real-world example of this?
Sure. Imagine a glass tumbler on a glass plate. If you try to pull the tumbler with a string, it'll slide easily. But if you wet both surfaces, they suddenly bind together, causing scratching. The water removes the contaminants, creating that strong glass-to-glass adhesion.
Wow, friction is way more complex than I ever thought. Like a whole hidden world of forces going on.
It really is. What's fascinating is that for how common friction is, our understanding of it is still evolving. There's so much more to uncover about the interplay of forces at those microscopic levels.
Makes you realize how much we take for granted. We were talking about those molecular forces that give rise to friction.
Yeah.
Can we dive a little deeper into those? They're like the forces between atoms, right?
Yes. Molecular forces are at the heart of how matter behaves.
Right.
To truly understand them, we'd need to venture into, quantum mechanics.
Whoa, heavy stuff.
Right. But even from a classical perspective, we can still glimpse their nature. Imagine, two atoms separated by a large distance.
Okay, two atoms far apart.
Would they attract each other, like with gravity?
I would think so, yeah. Like
That's
everything attracts everything else.
similar, but gravity is incredibly weak compared to these molecular forces.
Hmm.
The attraction between atoms at large distances, it varies inversely as the seventh power of the distance.
Seventh power.
That's
Yeah, that's a
right.
lot.
Right. But as they get closer, something dramatic happens. They start to repel each other
Mhm.
very strongly.
Ah, so that's what keeps us from, like, falling through the floor.
Exactly. It's this interplay of attraction at long distances and repulsion at short distances that allows matter to exist in these stable forms. At a certain equilibrium distance, the forces balance out and the atoms settle into a stable configuration.
So that's how solids are formed. The atoms are held together by those molecular forces, but also kept apart by the repulsion.
That's the basic idea. And this leads to another cool concept, Hooke's law. It states that for small distortions, the force needed to restore an object to its original shape is proportional to the distortion.
So like a spring, the more you stretch it, the harder it pulls back.
Precisely. Of course, Hooke's law has its limits. If you stretch or compress a spring too much, it'll deform permanently, and the law breaks down.
Right, right. Like there's a breaking point where the simple rules don't apply anymore.
Yeah.
So these molecular forces are responsible for things like elasticity. And they're also behind friction, even though we don't fully understand all the details right.
You got it. Now let's shift gears a bit and talk about another fundamental force, the electric force. This is where things get really interesting.
Electric force, as in electricity. Like what powers our home?
That's one manifestation of it. But at its core, the electric force is the interaction between charged particles. And like gravity, it can be described by an inverse square law. The force between two charges is proportional to the product of the charges and inversely proportional to the square of the distance between them.
Okay, seeing a pattern here. Inverse square laws, it seems like a recurring theme in physics.
It's remarkable, isn't it? These fundamental forces, they all seem to follow this elegant mathematical pattern. Now, there's a really useful concept for analyzing electric forces, the electric field.
A field, like a force field in those sci-fi movies.
Not quite. Think of it this way. A charge creates a sort of condition in the space around it.
Okay.
And this condition, it's the electric field. It's what exerts the force on other charges that enter that space.
So the field is like an intermediary between charges.
Yes, it lets us break down the interaction into two parts. A charge creates a field, and that field then acts on other charges. It might seem like just a different way of saying the same thing, but it's incredibly powerful for analyzing more complex situations.
So the field itself becomes a physical entity, in a way.
In a sense, yes. And this becomes even more apparent when we consider that interactions between charges, they aren't instantaneous. It takes time for the influence of one charge to reach another.
So the field carries, like, information about the past. Whoa, that's mind-blowing.
It really is amazing. And just as we have electric fields, we also have gravitational fields. We can apply the same concept. A mass creates a gravitational field around it, and that field exerts the force of gravity on other masses.
So when we talk about Earth's gravitational pull, we can think of it as Earth creating this gravitational field that we're interacting with.
Exactly. And just like with electric fields, the total gravitational field produced by multiple sources is simply the vector sum of the individual fields. This is known as the principle of superposition.
So we can just add up the fields from each source. Seems surprisingly straightforward.
That's the beauty of it. And this principle holds true for electric forces, even when charges are in motion. For gravity, things get a little more complicated when the field is super strong, like in Einstein's theory of general relativity. But for most everyday situations, the principle of superposition works perfectly fine.
So whether we're talking about planets orbiting a star or electrons whizzing around an atom, we can analyze these forces using the concept of a field. It's like a universal language for describing interactions.
Indeed, and it leads to some fascinating insights. For instance, we've been working under the assumption that the force of gravity from Earth is the same as if all its mass were concentrated at its center.
Okay. Yeah,
But is that really true? I mean, we're not at the center of the Earth after all.
yeah, that does seem kind of odd when you think about it.
Yeah.
Shouldn't the parts of the Earth closer to us exert a stronger pull?
It's a great question. The answer lies in the way gravitational fields add up. We can imagine Earth as being made up of countless tiny shells of mass. Each shell creates a gravitational field.
Right.
And when we add up the fields from all those shells, it turns out that for a point outside the Earth, the net gravitational field is indeed the same as if all of Earth's mass were concentrated at its center. It's a remarkable consequence of how gravity works.
Well, so that's why we can treat Earth as a point mass in our calculations. It's not just a simplification, it's actually accurate. That's really amazing.
Exactly. And it gets even more interesting when we consider a point inside the Earth. Like if we were to dig a tunnel deep into the Earth and measure the gravitational field there, we'd find something surprising.
Really? What would we find? Would the gravity be stronger?
Actually, the gravitational field inside a spherical shell of mass is zero. All the gravitational forces from different parts of the shell, they cancel each other out. This means that as we dig deeper into the Earth, the gravitational force doesn't just keep increasing indefinitely.
That's so counterintuitive. I would have thought the deeper you go, the stronger the pull would be.
It's one of those fascinating insights that comes from understanding how fields behave. Now, all this talk about forces and fields leads to another crucial concept: energy, and in particular, potential energy.
Ah, yes, energy.
Yeah.
Something we've been dancing around but haven't really tackled yet. What exactly is energy, and how does it relate to all these forces and fields?
Energy is, in a sense, the capacity to do work.
Okay.
And potential energy is a form of stored energy. It depends on an object's position or configuration.
So like a ball held high in the air has potential energy because of its position in Earth's gravitational field.
Exactly. And as it falls, that potential energy gets converted into kinetic energy, the energy of motion.
Right.
It's a great example of how energy can be transformed from one form to another.
Okay, I'm starting to get the picture. So potential energy out into.
That's a good way to think about it. And it turns out that for many forces, we can define a potential energy function. This function tells us how much potential energy an object has at a given position. For instance, for an object near Earth's surface, the potential energy is simply mjs sol. M is the object's mass, g is the acceleration due to gravity, and h is its height above some reference point.
So the higher the object, the more potential energy it has. Makes sense.
Yeah.
What about like that spring we talked about earlier?
For a spring, the potential energy is proportional to the square of its displacement from its equilibrium position. We can write it as haki-eksa, where ek is a constant that depends on the stiffness of the spring.
Okay.
So a stretched or compressed spring, it's storing potential energy ready to be released, like a coiled up reservoir of energy.
Exactly. Now, this concept of potential energy is particularly useful when we're dealing with conservative forces.
Yes.
Conservative forces, what are those? They have anything to do with politics.
Huh. Not in this context. A conservative force is one where the work done in moving an object between 2 points is independent of the path taken.
So it doesn't matter if you take a straight path or a curvy path, the work done is the same. Interesting.
Exactly. Gravity is a perfect example of a conservative force. Whether you lift an object straight up or carry it up a winding staircase, the work done against gravity is the same. Friction, on the other hand, is a non-conservative force.
Ah.
The work done by friction does depend on the path taken.
So friction is sort of wasting energy in a way that gravity isn't.
Well, it's not really wasted, but it's being converted into other forms of energy, like heat, that are harder to keep track of. For conservative forces, we can define a potential energy function, and this leads to a powerful principle: the conservation of mechanical energy.
Ah, conservation of energy. I've definitely heard that one before. It basically means energy can't be created or destroyed, right?
That's the general idea. But more specifically, for a system acted on by only conservative forces, the sum of the kinetic energy and potential energy stays constant. This principle gives us a powerful tool for analyzing motion.
So if an object is trading potential energy for kinetic energy, we can use this principle to figure out how its speed will change,
Yeah.
like a roller coaster going up and down hills.
Exactly. And this principle can be extended to systems of multiple objects. Like in a system of planets orbiting a star, the total energy, including the kinetic and potential energies of all the planets, remains constant.
That's incredible. So even in really complex systems, there's this underlying order, this conservation of energy, like a hidden harmony in the universe.
It really is. Now, you might be thinking, if all fundamental forces are conservative, what about things like friction, which we said is non-conservative? Does that somehow break the law of conservation of energy?
Yeah, that's a good point. If energy can't be created or destroyed, where does the energy lost to friction go?
Well, it turns out what we perceive as friction is actually the result of many, many tiny conservative forces acting at a microscopic level. When we rub our hands together, for example,
Yeah.
the kinetic energy of our hands isn't disappearing, it's being converted into the kinetic energy of the individual molecules in our hands, which we perceive as heat.
Ah, okay. So friction is like a hidden form of energy transfer. It's not truly disappearing, just changing forms in a way that's hard to see.
That's a great way to put it. And if we could account for all those microscopic interactions, we'd find that the total energy is indeed conserved.
Wow, so even in situations where it seems like energy is being lost, it's really just transforming into different forms.
Mm.
Reassuring to know that this fundamental law holds true even in those messy situations.
It is. The law of conservation of energy is one of the bedrock principles in physics, and it applies even in the most complex and chaotic systems. Now, we've talked about potential energy and fields, but how are these two concepts related?
Yeah, I was wondering about that too. They seem connected somehow, but I can't quite grasp how.
They are. It turns out we can actually derive the force acting on an object from its potential energy function.
Really?
The force is simply the negative gradient of the potential energy.
Gradient. Okay, that sounds a bit intimidating. What exactly does that mean?
It's a mathematical operation that tells us the direction and rate of change of a function. In this case, it means the force points in the direction of steepest decrease in potential energy.
So, like a ball rolling down a hill will always move in the direction where the slope is the steepest. Is that a good analogy?
That's an excellent analogy. And the steeper the slope, the stronger the force. We can write this relationship mathematically as F equals bioni u, where F is the force vector, u is the potential energy function, and esh is the gradient operator.
Okay, a lot of moving parts there, but I think I'm starting to see the connection. We can describe forces using fields, and we can relate those fields to potential energy functions. It's all starting to come together.
It is. These concepts form this beautiful tapestry that allows us to understand the workings of the universe at a deep level. And one of the most elegant examples of this is the parallel plate capacitor.
A capacitor, isn't that something you find in electronic circuits? I didn't realize it was connected to all this.
It is. A parallel plate capacitor is simply two parallel metal plates with opposite charges. We learned earlier that the electric field between those plates is constant.
Right.
And what about the potential energy? How does that play into this?
Yeah, good question.
The potential energy of a charge placed between the plates is simply proportional to its distance from one of the plates. And the difference in potential between the two plates, that's what we call the voltage.
Voltage. Now we're talking everyday language. So the voltage of a capacitor, it tells us about the difference in electric potential between those plates.
Exactly. And we can relate that voltage to the charge on the plates and the distance between them. The more charge we put on the plates, or the closer we bring them together, the higher the voltage.
So a capacitor is like a storehouse for electric potential energy, and the voltage is a measure of how much energy is stored. That's a good analogy.
That's an excellent way to think about it. And capacitors, they play a crucial role in all sorts of electronic devices, from storing energy in power supplies to filtering signals in radios.
Wow, so even something as seemingly mundane as a capacitor can reveal these profound connections between forces, fields, and energy. It's amazing how these concepts are woven into the fabric of our world.
It truly is fascinating, isn't it? And it's a reminder that even in the most everyday objects and phenomena, there are hidden depths waiting to be explored.
Welcome back to the Deep Dive Physics. It's amazing how much we've covered already, in parts 1 and 2.
From symmetry to vectors to all those forces and fields.
Right. It's mind-boggling when you think about how those concepts all connect.
It paints this picture of, like, the universe's underlying structure.
Absolutely. Something we talked about earlier that I've been thinking about are pseudo-forces.
Pseudo-forces.
Yeah, they seem kind of mysterious to me.
They're fascinating, really. They kind of pop up because of our perspective.
Okay.
They appear when we're looking at things from a non-inertial reference frame.
Non-inertial.
Basically, a frame that's accelerating.
So it's like when you're in a car that's speeding up or slowing down.
Exactly.
You feel that force pushing you back or forward, even though there's nothing actually putting or pulling on you.
Perfect example. That force you feel, it's a pseudo-force. It exists because your frame of reference, the car, is accelerating.
Right.
From an outside observer's perspective, you're just obeying Newton's laws.
Makes sense.
But from your perspective inside the car, it feels like this extra force is at play.
It's all a matter of perspective then.
In a way, yes. Another classic example is centrifugal force.
Ah.
When you're on a merry-go-round, you feel that force pushing you outwards.
Right. You're going to fly off.
Exactly. But from an observer standing on the ground, you're just moving in a circle because of the inward force from the merry-go-round.
So centrifugal force isn't really a real force then. It's just an illusion.
Precisely. It's an illusion created by being in that rotating reference frame.
Okay, I see.
And here's something interesting. These pseudo-forces, they're always proportional to the mass of the object experiencing them.
Just like gravity.
You got it.
Wait a minute. Are you saying that gravity itself could be a pseudo-force?
That's a question that really fascinated Einstein. It led him to his theory of general relativity.
General relativity, whoa.
He basically proposed that gravity isn't a force in the traditional sense.
And what is it?
It's a consequence of the curvature of spacetime caused by mass and energy.
Curvature of space-time. Okay, you're going to have to break that down for me.
It's definitely a mind-bending concept, but the basic idea is massive objects like stars and planets, they warp the fabric of spacetime around them.
Okay, I'm listening.
And this warping, it's what we perceive as gravity. Imagine like a bowling ball on a trampoline.
Okay, yeah, I've seen that demonstration.
The ball, it creates this dip in the fabric, and if you roll a marble nearby, it'll curve inward towards the bowling ball.
Right, like it's being pulled in.
Exactly. So instead of Earth pulling on us with a gravitational force, it's actually warping space-time around it, and that's what causes us to fall towards it.
So gravity is like a cosmic illusion, a trick of space-time.
You could say that. It's a fundamentally different way of looking at this force that shapes our universe. And it all comes from, shifting our perspective.
Challenging your assumptions.
Exactly.
Wow, this has been an incredible journey. We started with simple concepts like symmetry and ended up exploring the curvature of spacetime.
It really highlights how all these ideas in physics connect.
From vectors and forces to fields and energy, even general relativity, we've covered so much. It's like I have this whole new appreciation for the universe now.
That's what physics is all about, right?
Yeah.
Unraveling the mysteries and finding those beautiful patterns that are hidden everywhere.
Well said. And thank you for joining us on this incredible deep dive into the world of physics. It's been a wild ride.
It has. And thank you for listening to the deep dive.
We'll catch you on the next one.